All right, thanks a lot, and thanks to Mengdi and Sanjeev as well for organizing this workshop. I'm very happy to actually follow up Sergey's talk because many of the issues I'm going to touch upon today are really mathematical issues involved in some of the things Sergey discussed. And in the spirit of this workshop being new directions, definitely feel free to ask questions during the talk. I'll just repeat them because some of the main ideas I'm going to present are really going to give perhaps some different perspectives, so feel free to ask questions. Okay, so quickly going through the start, we're clearly here because we value the importance of interactive learning in many disciplines relevant for scientific domains and technological domains. And reinforcement learning is really the natural formalism for sequential decision making in which we want an agent to take some course of actions to obtain some long-term objectives. Okay, so we're going to be working with the standard MVP framework, which people are familiar with, but just in terms of notation, we're going to have some policy, which is a mapping from states to actions. We're going to execute a policy for 8 steps in the environment. The value of a particular policy starting from state S0 is just the total sum undiscounted reward for what the agent achieves when that policy is executed starting in S0. Okay, our goal is to find this behavioral policy, this mapping from states to action that maximizes this cumulative reward starting from some given start state. Okay, and that's the very natural way to think about the world in that picture. Okay, and just in terms of notation, we're going to say S is our number of states. Think of the number of states as being large or infinite. A is the number of actions, and H is the horizon. Okay, and quickly reviewing some of the challenges that we face in reinforcement learning, we're familiar with this problem of exploration, that we might not know the environment, so our agent's going to wander around and need to gather information. It can't waste too much time doing this because it also wants to obtain a reward. There's this credit assignment problem. If our agent hits -1, how does it figure out what it did wrong with regards to actions it had taken in the past? Okay. And of course, we have to deal with large state and action spaces. So this is this OpenAI demo from a couple of weeks ago, which many of us think is pretty impressive because dealing with dexterous hand manipulation is challenging due to large state and action spaces, dealing with contact forces, and possible issues in terms of making sure a simulator is good enough so it actually transfers, at least in some way, to the real world. So there are many, many issues here. And let's step back a moment and look at the classical solution for this concept and think about how we're going to, for planning, and think about what this means for the problems we care about. So the classical solution is this dynamic programming approach. So think about a very large table where the first column is the possible states in the world. So in that last example, you can think of a state as consisting of the joint angles in the robotic fingers, and maybe the cube configuration. We can think about the action as the forces that are going to be applied at the actuators at the various joints. They're clearly continuous, so this table is infinite. And the way the classical dynamic programming approach is going to work is it's an iterative algorithm where this last column is going to keep track of the state action values. You can think about this as like a one-step look ahead. So we start with some policy pi. This state action value is we're in state S, we take action A, and what's the next future value we get after we do that? Okay, so it's like a one-step look ahead value. So the way this algorithm proceeds is that for every row in this table, we're going to figure out this one-step look-ahead value. Once we have that, we're going to update the policy in some greedy manner and iterate. Okay, and if we do this exactly, this algorithm will converge in H steps. Okay, but of course, this table is infinite, and we might not even know the dynamics in the world. And there's a question of how do we handle this infinite table? Okay, and often we're appealing to various sampling or supervised learning approaches. Okay, so what are the differences from supervised learning? Well, in supervised learning, we're basically told the correct action. So in that last table, someone's just going to tell us this is correct or not. And we're given a distribution over states in supervised learning, whereas in RL, the distribution over the states is going to be determined by the current policy we're executing. Okay, so deep RL. One way to tackle this infinite table, as Sergey mentioned, is we've made a lot of progress in our ability to do learning in these supervised settings and to build representation in these supervised learnings which generalize. And we can think of deep RL as the approach of trying to use our successes with neural network learning to bring them over to reinforcement learning to essentially deal with this large and infinite table. Okay, and the approach in deep RL is typically some type of method which transforms our input into some type of low-dimensional feature representation, where that feature representation is helpful for the task of interest. Okay, and these methods often jointly learn this feature representation phi and the classifier. Okay, and this deep RL approach is to try to bring in our successes in this non-interactive setting into the more interactive learning domain of reinforcement learning. PowerPoint is not responding. Looks like I might have crashed. Strange. Give me one sec. Try it again. Very good. Okay, good. So what this talk is going to be about is we're going to start looking at necessary conditions in which generalization is possible to deal with this infinite table. So there's a lot of work on sufficient conditions for generalization. So we're really going to do a whirlwind tour and a little more of a technical tour of what are the conditions which permit, what are sufficient conditions which permit generalization. So we're going to start with this review. Then we're going to start asking what might be necessary conditions for generalization. And we'll talk about some related issues at the end and maybe an open problem. Okay, so throughout the talk, there's a question of what access do we have to an MDP. And we're going to go back and forth between two models. We're going to work with, so the most general setting might be this, something closer to this episodic setting, where we start at S0, we act for 8 steps, and then we reset back to S0. But we could also work in this model, in the setting where we have a simulator or a generative model. And that's for every state action pair, we're going to get a sample of the next state and the reward. Okay, so there's 2 interactive models we're going to consider, which is the episodic one and the generative model setting. And we're going to move back and forth between them. Okay, so let's start by doing a tour of how we think about generalization. Actually, before that, let's take a step back. Forget about generalization. Let's just make sure we're on the same page with regards to approximation, and if we just ran this exact algorithm of dynamic programming with errors. Okay, so suppose for a moment we're going to run this iterative algorithm, but we're going to have errors in it. Okay, and let's look at essentially what's known with regards to worst case errors. So what you're going to need for this algorithm to work if there are errors is a very stringent condition, which is entry-wise, every entry in that table, suppose you get it correct to within epsilon. So this is a very, very stringent condition. So this is literally worst case entry-wise error of epsilon. But suppose we manage to do that, then, and we run this algorithm, then after 8 steps, we're going to find a policy which is close to the truth, which only has some type of polynomial blow-up on the factor of epsilon. So what we get when we run this algorithm for 8 steps is essentially degradation that's the horizon squared times the error. Okay, so that's approximation. And with regards to supervised learning, this looks already pessimistic because it's very hard to get algorithms which guarantee worst case error with our standard way of thinking about supervised learning. Okay, but that seems to be what we need for RL without further assumptions. Okay, so that's approximation. Now let's start thinking about generalization. We're going to really do a whirlwind tour of what's known with regards to upper bounds, and then we're going to start asking the question of what might be necessary. Because I think people who come into RL, or certainly those who are in it, they might find it a little odd for how many assumptions people make in this setting to get various results to work out. Okay, and when we do that, it's important to take the flip side of trying to understand why are we making these assumptions, and that might give us intuition as to what are the reasons for which reinforcement learning is difficult. Okay, so again, this is definitely a bit of a whirlwind tour of both of these topics, and I will be a little more technical here. So let's actually start with generalization in the supervised learning setting. And Sergey actually touched upon these issues, but I'm going to touch upon them in more of from a technical perspective. Okay, so generalization in supervised learning. This is the setting where we get data in some IID manner. Okay, and we're going to have some hypothesis class. And the goal is to try to get some small number of samples so that we'll do well on new data. Okay, that's a classic generalization question. And suppose we want our generalization error to be epsilon. Okay, so the starting result here is what's sometimes known as this Occam's razor bound. So if our function class is finite, it's actually great in that our dependence on the cardinality of our hypothesis class is only logarithmic. Right? And in a sense, this is really the foundation for generalization in supervised learning because we can deal with very, very large hypothesis spaces. Again, based on that, there's various VC results where you can extend it to other notions of complexity. So this is the celebrated result due to Vopnik and Chernovenkis. And then we have spent a lot of time looking at computational and statistical issues in special cases. For example, for classification, if our data are linearly separable and we have a margin, we can generalize with margin over epsilon squared. If we're doing linear regression in d dimensions, we can also generalize with the number of samples that's d over epsilon. And we're even starting to get some ideas about deep learning. Okay, so this is the kind of whirlwind tour of generalization in supervised learning. Definitely ask questions, come and move into RL in a moment. But the key idea in supervised learning is this issue of data reuse. In supervised learning, when you have your data set, you can simultaneously figure out how accurate multiple classifiers are on this data set. I can try one classifier, I get an estimate of its error, then I can try another classifier, and so on. And in reinforcement learning, the fundamental difficulty is it's not easy to do this. So suppose we have a class of policies or a class of behaviors. How do we simultaneously figure out how good a different policy is? Because maybe we collected our data in some way, and we just don't see any states where a different policy will visit. Okay? And that's really the fundamental issue here in reinforcement learning. Okay, so how we thought about generalization in RL, where we actually want to deal with very large policy classes and high-dimensional state spaces. Okay, so we'll go through a quick tour of how we think about generalization in RL. Okay, so probably the most basic one is, look, if I want to reutilize my data, how about I just act randomly and try to do importance sampling? Okay, because the idea now is if I act randomly, so I start at S0, I just act randomly for 8 steps, so repeat, and then act randomly again. Okay, and now I can use importance sampling. So now for every policy, I can get an estimate of how good it is with importance sampling. Okay, and this is this really fundamental result due to Kearns, Mansour, and Ng called the trajectory tree approach, which is really just importance sampling. Suppose for a moment there are 2 actions. And the point now is that if you did this, you can actually simultaneously estimate how good all your policies are. And what's nice about this is you only, like supervised learning, will only depend logarithmically on the number of policies in a policy class. Okay? But the drawback now is we pay 2 to the h. okay, because of this importance sampling. But it's much like supervised learning because we are logarithmic in the size of a policy class. Again, there are various notions. You can extend it to VC sorts of ideas. Okay, and in a sense, you can think of much of RL as generalization in RL as trying to avoid this 2 to the h. Okay, because note there's no dependence here on the number of states in the world, similar to supervised learning. Okay, so this is really the starting point for thinking about generalization in RL. Okay, then how do we move beyond that? Really, after that, we just explore lots of different assumptions for when we can avoid either an explicit dependence on the number of states in the world or an explicit dependence on an explicit exponential dependence on the horizon. Okay, so a few of the results are, for example, we can assume that this optimal state action value, this optimal one-step look ahead, if it's the case that that is a linear function with some known feature mapping and our MDP is deterministic, then we're good. Okay, then there's an algorithm that does it. And recently, there's a weakening of those assumptions. But this is one special case. Perhaps some of the most general conditions are these ideas of Bellman rank and witness rank from some of the MSR folks. And that includes some special cases which we've heard about here. We heard about the linear MDPs, which is a special case of this Bellman rank. So Mengdi gave a very nice talk about an efficient algorithm for dealing with linear MDPs, which is really a setting where our transition matrix is low rank, and the rewards live in the range of this matrix. So this is basically the setting Mengdi was working in. And you can get a polynomial sample complexity. John spoke about essentially block MDPs, which can also be viewed as a special case, though the issues are a bit different. Okay, so we do kind of make various assumptions to try to deal with this. But note, if you just look at this, it takes a while to understand what's going on here. But they all avoid the explicit dependence on the number of states in the world, and they avoid this 2 to the h. There's another class of algorithms based on policy search which avoids the 2 to the h. So this conservative policy iteration is one such algorithm. And the spirit is, if we had, for example, some starting state distribution which was good, we can get better dependencies. I'm not going to go too much into detail into this, but those of you familiar with the literature, there's a way to try to avoid this 2 to the h if we make assumptions with regards to having some idea where an optimal policy might tend to visit. And that's one way to avoid. Imitation learning is one such special case. And this algorithm John referred to, policy search by dynamic programming, is a special case. Okay, so this is clearly like a very fast tour of many, many results looking at generalization in RL, and I think I've convinced you that it's not an easy thing to do because the naive approach to deal with generalization is just importance sampling, then we can reutilize our data, but we pay a 2 to the h factor. And everything after that tends to be, in a sense, when you come into it, it might look like a lot of complicated assumptions, like why are we making all of these assumptions to generalize? Okay, and that begs the question of what's actually needed to generalize in RL. Okay, and we're not going to precisely give necessary and sufficient conditions, but I think it's helpful to start thinking about lower bounds to see why we're making various assumptions in our upper bounds. Okay, and that might also give us intuition for what type of heuristics are reasonable to consider. Okay, so are there any questions so far? So we're going to really consider two natural assumptions, which is with regards to how well we can approximate the value functions and how well we can approximate policies. Okay, so if we go back, here, remember that with regards to approximation, if it's possible to get a worst case approximation at every step, we're in good shape. Like if we can actually achieve that, which is a super stringent condition, and my own viewpoint is the difficulty of reinforcement learning was that this condition is way too stringent, that it just seems unreasonable to get supervised learning to deal with worst case approximation. Okay, so remember that. Turns out the situation is much, much worse. Okay, so now let's start with actually a strong assumption, and I'm just going to give us the ability to get good worst case approximation. So let's go ahead and assume that for every policy, we have some low dimensional feature representation phi. So phi lives in d dimensions. Think of d as being much, much smaller than the state space, which could be infinite. Okay, so for every policy, including the optimal one, there exists a good linear worst case approximation to it. So this is clearly a super, super strong assumption. Okay, it's going to be less than epsilon. Okay, and the dimension is going to be relatively small. It's like 1 over epsilon squared. Okay, so now we have the ability to do worst case approximation. Okay, and now I'm going to claim even with this, we don't get this amplification that's like h squared. Okay, so we would hope that with this, we could actually generalize and do RL. In particular, what are we hoping for? We're hoping for something information theoretic where we only depend polynomial on the dimension and the horizon. Okay, so the first result is actually this is impossible, that there exists a class of MDPs where the optimal value in the MDP is 1, and if we just wanted to get a value which is bigger than a half, it's actually going to require exponentially many trajectories in the planning horizon h. Okay, and think of epsilon being small. Okay, and why is this surprising? Well, suppose we actually found the W that achieved that condition, then the amplification would be just h squared epsilon, because that's what we showed before from this approximate dynamic programming approach. Okay, so now I've given us the ability to do this. And our sample complexity, so this is information theoretic, we actually need 2 to the h samples to do this. Okay, so in a sense, the situation is far worse than just depending on this infinity norm error, because now we have the ability to get good infinity norm error. And if we really achieve that, we would have gotten h squared epsilon. But the point is, somehow, something's going wrong information theoretically. So at some level, this feels like hopeless. I'll come back to implications in a moment. Because the dimension here isn't even that large. Okay, so what's the construction? Well, what's the intuition first? So what's the reason for the hardness? Well, in the construction, it's not really going to be due to exploration of the dynamics in the usual sense, because we're actually going to get to know the underlying dynamics in the world in this construction. It's just the reward function we don't know. And our representation, again, is near perfect, because it is this for every single policy in the world, we have a good worst case approximation with a low dimensional space. And what I think is appealing about this lower bound, sometimes lower bounds are pathological and might not say something about reality. What's interesting here is that when you look at this construction, this is not a pathological instance. There's a sense in which almost all feature mappings will lead to this hard instance. So I actually think this lower bound is very revealing to some of the difficulties we're facing in practice. Okay, so what's the construction? Well, the world is going to be a binary tree with, say, about 2 to the h states, two actions. And suppose we know it's a tree, only one of the leaves are rewarding. Okay, and suppose we know it's a tree, we know the labeling of the nodes. If we don't know the reward function, forget about function approximation. If we don't know the reward function, we clearly require 2 to the h queries, because we've got to visit every leaf node. It takes 2 to the h. Okay, so now there's this pretty simple observation that I think they do this a lot in CS theory. They're trying to find a good low-rank approximation to the identity function in a spectral sense. But basically, with a randomized construction, you can well approximate the value function in a uniform sense for every policy using JL. Okay, so every policy you can uniformly approximate. And the key thing is I can build my features independently of seeing the dynamics and the rewards. Okay? So the point now is like, look, if you told me you could do the previous problem, then you could have generated the features on your own without even interacting with the world and solve this problem. Right? Because the features here are constructed in a way that has nothing to do with the class of MDPs, the random features. Okay, so random features are actually pretty, in a nutshell, random features are pretty good for supervised learning. They're going to approximate the value function, and we're not going to be able to solve this. Okay, so that's really the construction. You can look at this offline. I'll talk about implications in a moment. So one thing to point out is, look, this is for linear mappings, but neural nets are a superset of linear mappings. So this doesn't bode well for neural nets either. Okay, so the second hardness result is, this was an assumption more like in the spirit of linear regression, which is widely considered in the reinforcement learning literature, which is suppose we had a good linear representation. Now let's consider an assumption more in the spirit of classification. So suppose the optimal policy now, not every policy, suppose the optimal policy could be represented as a linear classifier of the following form. So it's just the argmax for some W in some known feature space. Okay, so that's our, so this should be pi star of S. So the choice we make, the choice of action we take at state S is this kind of argmax. Okay. Let's suppose this optimal policy has a margin. So that's the nice sort of assumption we make in classification. Furthermore, let's make this a nice looking problem where the MDP has a gap, meaning the value of the best action in every state is significantly better than the second best action. Okay, so it's not like there's two actions you might be slightly confused about. The best action really has value much better than the second best action. So there's a nice non-trivial gap, and this optimal policy has a margin. Okay. For supervised learning, this would be great. This is all of the perceptron algorithms, margin bounds, and so on. And we get computationally efficient algorithms under this assumption. Okay, but in RL, same thing. It's a different construction here, but you actually need exponential and h many trajectories to do well on this problem. Okay, so I think both of these start giving us some insight into why we need these types of more complicated assumptions, because the most natural analogs of the types of things which make supervised learning easy tend to break in RL for somewhat subtle reasons. Okay, questions? I'm not going to go into the construction of this one. It's really just something to do with geometry and volumes. But note, of course, this is completely consistent with supervised learning, because when h equals 1, we're all good. Okay, so what are the implications of this? So this is, again, maybe my own perspective on this. But it does give us insight into what types of deep RL algorithms might be successful. Okay, and in particular, at least the value-based assumption, this was really just reward-based. And if you think about algorithm like posterior sampling, this is you're trying to just force the agent to explore by jittering the parameters to capture uncertainty in the value functions. And there's a sense in which, what's going wrong with this lower bound? What's going wrong with the lower bound is that we're very, very good at supervised learning. That on any fixed distribution, you'll actually approximate the optimal value function very well, but that's not going to give us the ability to do transfer learning. Okay, and if we're thinking about learning features in a purely reward-driven way, this does not bode well for algorithms like posterior sampling, which are entirely reward-driven in the way they construct their representations. Okay? And my own personal takeaway is that this really does suggest, if we think about what types of assumptions avoid this lower bound, they're typically methods where the representation actually captures something about how the world works, which is not something we typically do in supervised learning. Supervised learning, ignore the way the world works, build a neural network. Whereas the types of assumptions that might avoid this lower bound in RL are methods in which the way we might try to build the representation has something to do with the dynamics. So, these random distillation networks, which seem more plausible. In theory, essentially all of the provable methods that we have either make explicit or implicit assumptions about the underlying model dynamics in the world. So that's more than just these agnostic types of assumptions. And there might be other ways to do this based on some work I did with Alon, Karan, and Abby here, where you're trying to visit new states, which is, again, you're constructing fictitious problems based on properties of the dynamics in the environment. Yes?
How much of this is coming from having super sparse rewards?
Good question. So it's easy to fix this and not having sparse rewards. So it's not really super sparse rewards. I would say it's really due to transfer learning, that if you actually had a horizon you cared about. See, somehow what's happening in supervised learning, we're fitting under one distribution. It's very hard for us to get a guarantee that this is going to do well on a different distribution. And that's what having features that say something about the dynamics allows us to do. So it's not really sparse rewards per se. It's actually, I would argue, it's something closer to transfer learning is what's going on. Which I would say is actually, at some level it's a little disheartening. I find it maybe a little heartening because, shocking, I know, but maybe we should learn something about the world if we're going to interact with it. But we've never seen this being super important in supervised learning, but more and more we're seeing in RL that this might actually be important. The rub is I also don't like building models of the world because aside from robotics, this can get very, very, very brittle sometimes. And this intuition isn't entirely true because something's a little fishy about MDPs with deterministic dynamics. Because when the MDPs have deterministic dynamics, again, that's clearly an assumption about the world. The dynamics are deterministic. But some of these methods, like linear MDPs, they break for deterministic MDPs. They just don't work. So it's worthwhile to consider various types of assumptions of the dynamics to gain intuition for what's going on. And I'd be happy to discuss things offline. Okay, so let's see. I started. We've got about 10 minutes. So questions there? So I do want to touch upon an open problem related to Sergey's talk as well on, we're talking about generalization here. And the issue of generalization is really sample efficiency, right? We collect some data in various manners, and we want to be sample efficient. Okay, and a super basic question is, what is the most sample efficient class of methods, and are those model-based or model-free? Okay, and this was really a question that I started formalizing in my thesis in various different settings. But perhaps the simplest abstraction to ask this question is in this of a generative model, where you can give it a state action pair and you get a sampled reward in next state. Okay, so if you can't understand the most sample efficient method here in a tabular case, we're really doomed. Okay, and in this very simple case of having a generative model, we can ask, what is the most sample efficient procedure? And for that most sample efficient procedure, should we build a model of the world, things like, related to what Sergey was talking about, and this is a classic question, or should we somehow just directly learn how to act? Okay. The advantage of building a model of the world is it permits data reuse. Okay, so let's quickly go through the history of results here and end with an open problem. Okay, so the first major result here was due to, again, Kearns and Singh, that they showed that these two approaches are comparable up to essentially polynomial factors in the horizon. And a really, really nice result due to Azar and co. Showed that if I just care about estimating the values, the sample complexity was just linear in S and A and h cubed in the horizon. The problem was that was only for value estimation, but for actually getting a good policy, it was worse by a factor of h. There seemed to be some amplification going on. And there's a real question of, is this real? Okay. Then with Mengdi here and various colleagues, they had an extremely nice result showing that there was a model-free approach where they didn't reutilize data, so they did things in phases, throwing away data, and a very clever way to do variance reduction. That was the first method which truly got the minimax optimal rate. And it was actually throwing away data because they were concerned about the basic concern is, are you chasing your tail somehow, following the errors in your sampled model? Okay. And this kind of left this question of, at least in this generative model setting, can you literally just build a model of the world and plan it and have that be optimal? Or does something go wrong where you actually need to do some kind of sample splitting to make it optimal? Okay, so then recently, we actually resolved this, showing that, in fact, it was entirely an analysis issue. So for a while, I was trying to prove a lower bound, showing that maybe a model-based approach would be worked. And I think we spent quite a while trying to come up with a lower bound until we realized it was an analysis issue. And the simplest model-based approach of just drawing samples uniformly from this generative model, take the empirical model, use any efficient algorithm to find the optimal policy, that would be sample efficient. So at some fundamental level, they're really essentially up to log factors. There should not be a difference between model-based and model-free. And the log factors, I think the model-based clearly wins for. Okay. But again, this is in this very idealized setting where we have a generative model. Okay. So the setting we care about is we're collecting data adaptively in the world, and we can't just input an essay pair and get a next sample. We actually have to interact with the world to gather samples, and we'd like to understand data reuse in settings where we adaptively collect samples. Okay, and here there's actually an important technical open question. So let me just review. Good, I've got like 5 minutes. Let me just review the state of the world here. Emma talked about this a bit. So this is the setting where we care about regret. We don't have a general model. We start at S0, act for 8 steps, and reset. Okay, or in the discounted case. Okay, so there's the model-based approaches, again, starting with a different line of work due to Kearns and Singh, and by various other people. For all of the model-based approaches, you only get something non-trivial when you collect at least order s² samples. For these bounds to be non-trivial, meaning less than 1 in terms of your regret, you have to have collected order s² samples. Okay? And that's pretty bad, because at s² samples, you actually have a pretty good idea of how the world works. Okay? But the recent results, essentially due to like Azar, Chris Dan, and so on, asymptotically, it's not s², but we actually care about finite rates here. And all of the results in the model-based land, for them to kick in, you actually have to have order s² samples. Okay, so now we can go to the model-free approaches. The first result here for Q-letting that was provable was really due to Strail. There was some nice improvement due to Chi-Jin here, improving some dependencies, but the first provable result for Q-letting was really this phased Q-letting algorithm. So what's nice about this model-free approaches is we can actually get sublinear regret with a number of samples that's only O of S. Right? So the number of steps you need to act in the world, which is T here, only needs to be order S before you get non-trivial regret. Okay, so all of our model-free approaches when you do the analysis correctly, give us sublinear regret when a number of samples is only O of S. And they give us regret less than 1. They kick in when our regret only needs something like order S samples. But the horizon dependence is incorrect. Okay? And this is a real issue because they're actually not reutilizing samples. So the concern with this bottom class of algorithms is they're actually sample inefficient because they keep throwing away samples. But they're nice in terms of their S dependence. Okay? So the open question here is, can we get something non-asymptotically minimax optimal that kicks in before we have a good model of the world? Okay, and an even simpler question, so our conjecture is the model-based approaches are fine, but an even simpler question here is, can we actually handle data reuse in model-based approaches and get any regret bound that's poly H that looks like that? Because the problem is somehow when you do the analysis in the model-based approaches, you can't do anything until you get order S squared samples. And it really seems like a probability theory question. I think this is a very important question because it's a question of data reuse. So if we don't understand how to do data reuse in even this simple tabular case, it doesn't bode well for these more complicated settings. Okay? And maybe there's a lower bound showing it's real. My conjecture is no. But I think it's important to resolve. Okay, so in a nutshell, look, we're clearly seeing a lot of progress in reinforcement learning and deep RL, which is how we deal with this infinite table. I discussed some of the representational issues, which perhaps gives a bit of new perspectives into why we're making various assumptions to get generalization in RL. Also discussed some questions about model-based versus model-free learning and an open question, which, again, that open question is really for theory people and probabilists, but I think it's a really great open question that would help in many other settings. And I think as we've seen from these talks that in RL, having like more provable algorithms really might lead to better practical algorithms, because this approach of just lifting simple algorithms which work in a tabular case to the general case is fraught with a lot of difficulties. And this is joint work with a lot of great people, many of whom are here at the event. Thank you very much.